All right, everybody. So 2.4 chain rule. This is derivatives. Just a quick refresher. Recall the derivative rules that we know about so far. Derivative rules we know so far. We know the power rule. That was d dx of x to the n is nx to the n minus 1. Right? You take the exponent, bring it down in front, and reduce it by 1. This also applies to fractions, negative exponents, any kind of exponents. Fraction exponents, which are radicals, any exponents, use this power rule. We have the product rule. Which was if we do a derivative of f times, that's going to be first times the derivative of the second, plus the second, plus the second times the derivative of the first. fg prime plus gf prime. Product rule. Remembering these rules about derivatives. The quotient rule, which was if we did a derivative of two functions dividing each other, that was a little phrase, low d high minus high d low over low squared. Low d high minus high d low over low squared. Typically that's put in parentheses. So the quotient rule that we had for our derivative. And these were the main rules we had so far. We're going to add one more rule here. This is going to be called the chain rule. Chain rule. And the chain rule is when you're doing a derivative of a function that's inside another function. F of g of x. Let me write this a little bit. A function inside a function. It's a composition of functions. F of g of x. When you have a composition of functions, one function inside another, I'll show you some examples of what that looks like. The derivative goes like this. You do the derivative of the outside, leaving the inside alone, derivative of the outside, times the derivative of the inside. Let me say that again. Chain rule says you do the derivative of the outside, f prime, leaving the inside alone, times the derivative of the inside. Let me give you some examples of what this looks like. Say I have a function that's like this. 2x squared plus 3 to the third power. This is a kind of function that has like 2 layers. Right? Inside, you can think of this 2x squared plus 3 as your inside function. 2x squared plus 3. Right? Because it's inside this parentheses. That is a function in and of itself. 2x squared plus 3. Outside, we have this function that's cubed. Outside is something cubed. And that is another function, right, that we can do a derivative of. That's a power rule. There's this outside function and this inside function, right? We have this outside function of this cube part, and then this inside that's being cubed, this other function that's inside. So if I was to do the derivative of this, d dx of 2x squared plus 3 cubed, I would do the derivative of the outside first, leaving the inside alone. So the derivative of the outside is the cube function. So I'm going to do my power rule to like the whole thing. So that's going to be 3 times blah, blah, blah squared. I do not change the inside at all. This is going to stay 2x squared plus 3. So that's the derivative of the outside. I did my power rule. The 3 goes in front, reduce the exponent by 2. I don't deal with the inside yet. It's like you're covering it up. You're like covering this part up. You're just doing the derivative of the outside function. Derivative of the outside function first. Then you multiply that times, or sometimes parentheses, the derivative of the inside function. Now we look at this 2x squared and I do the derivative of this 2x squared plus 3. Derivative of the inside. The derivative of the inside part, I ignore the cube now, just looking at the inside. And I'm going to do a power rule again. This 2 goes on, so 2 times 2, that'll be 4x to the first power. And the derivative of 3 goes away. And so that's my derivative of the inside. So derivative of the outside times derivative of the inside. That's how I do my chain rule. And this is my answer. This is completely acceptable. This is totally fine. If I want to simplify this, I could do a little bit, right? This 4x times 3 is all on the outside part, right? So I can multiply 4 times 3. That would be 12x. 12x times 2x squared plus 3 squared. And that would be my derivative. Supposed to be a 2. I don't know what happened there. Squared. That would be my derivative. Okay? So using the chain rule, connecting all these functions together. Let me see, I'm looking for another example. That'd be good. Okay, here's a good one. All right, here's a good one. Another example. What if I had something like the following? It's just box right here. So the outside is F, the inside is G. Correct. You can think of it that way. For sure, Jessica. The outside is F, the inside is G. Yeah, let me maybe say that here. Outside. And this G is the inside. So it's the derivative of the outside where you leave the inside by itself and then multiply by the derivative of the inside part. All right, another example. What if I had, let's say, the cube root of x squared plus 2x minus 3 squared. So I have this function here. F of x equals that. The cube root of x squared plus 2x minus 3 squared. How do I do this one? There's a couple ways we can think about it. What's my outside? What's my inside? What's my answer? Well, one way you can think of it like, okay, this square root, this whole square root's my outside part. Right? That square root's my outside part, and this whole thing squared is the inside part. That's one way we can do it. And then this inside part also has another inside part. So we can chain together the chain rule as many times as we want. It works the same way every time. You can use the chain rule multiple times. So we can like do a chain rule and then a chain rule and then a chain rule. We keep going down the chain, like doing the derivative of the outside times the inside. Derivative of the outside times the derivative of the inside, right? And then we go inside, and we just keep going down the chain as many times as we need till we have our smallest function. So let's try doing this one. Let's do the derivative of this one. F prime. If we do d dx of this, well, we know that this cube root is the same as a power rule. So we can say that this is the same thing as 2x squared plus 2x minus 3 squared to the power of 1/3. That's the same thing, right? So if we do the chain rule for this, we do the derivative of the outside, the radical part, the 1/3 part, put the 1/3 in front, 1/3 times, we leave everything, the whole inside part, completely the same. We leave it untouched. Right? We don't touch the inside part at all. Just doing the derivative of the outside part. Bring the 1/3 down, 1/3 minus 1, that's going to be negative 2/3, right? 1/3 minus 1. Remember what I said about like doing subtraction with fractions? 1/3 minus 1 is the same as 1 minus 1/3. If I have a whole, I take away a third, it's going to be 2/3 left over, but it's negative 2/3 because I'm minusing the 1, right? That little trick. 1/3 minus 1, negative 2/3. So that's the derivative of the outside. I didn't touch the inside at all. Didn't touch it at all. Now I touch it. Now I do my derivative of the inside. The outside times derivative of the inside. So now I'm going to do the derivative of this one. But here we also have another chain rule. So the derivative of the inside is going to be the derivative of the outside of the inside, the squared part, times the derivative of the inside part, right? So I'm like layering my chain rule. So I did the derivative of the outside, that's the 1/3 up front, negative 2/3, times the derivative of this inside. The derivative of this inside part, I'm only going to look at this function here now. And I notice that this function here requires another chain rule. So I'm going to go chain rule here, 2 times, leaving this inside part, my new inside part alone, to the power of 1, right? I did my derivative of this outside part, the squared part here. I did that in front and multiplied by this inside part. Just left it alone because that's my new inside part. Derivative of the outside times derivative of the inside. Now I have this derivative. I did my derivative of this outside times the derivative of my new inside, my real inside, the inside, this one here. So that derivative is going to be 2x plus 2. And that's my whole chain rule laid out. So I layer my derivative, I layer my chain rule, right? So let's see, if I have my outside, this is my outside, is that cube, and then I've got like another inside, which is the squared, right? The inside one. And then I've got a more inside part here, right? This is my third inside squared, inside times 2, right? Or whatever. My double inside. So I did the derivative of the outside, right? Here's the derivative of the outside. Derivative of outside times the derivative of inside, oopsies, the derivative of inside 1 times the derivative of inside 2. Double inside. So we can like layer our chain rule. We can sort of keep going as many times as we need to with this chain rule. 3, 4, 5, 6 times. I mean, like as many times as hopefully there's no craziness on the AP test. But if there is, you know how to deal with it. You just keep going. Just derivative of the outside times derivative of the inside. If the inside has another layer, like an onion, just keep peeling it away. Do the derivative of the outside times the new inside. Okay, then do that derivative of the outside times the new inside. Just keep going. Just keep going down the chain. Okay? Okay, everybody? We could do some simplifying here if we really wanted to. Maybe important. Let's see. I have a 1. How did I get the 2x plus 2? It's like an onion is making, oh, party style. That was a good joke. That was a good joke. Where did this 2x plus 2 come from, you're asking? This 2x plus 2 is the derivative of this inside part here. This here, right? I brought the power rule. I did the 2 in front times x, right? That was 2x. Plus the derivative of 2x is just the 2, and the 3 goes away. Yeah, so we did the derivative of the outside, the first outside, which is the 1/3, times the next derivative of the outside, which was the squared part, right, that 2 in front, and there was no more exponent here, times the next derivative of the inside, this part here. Let's see if we can simplify this, everyone. I got a 1 on top, I got a 3 on the bottom. On my denominator, I have a 3, and then this negative exponent, so this whole business here, of x squared plus 2x minus 3 squared to the 2/3 is going to go here on the bottom. Because that was a negative exponent, right? That goes down there. On the top, I've got all this stuff here. I've got a 2. Okay, so this is going to be a 2 on the outside here. Times x squared plus 2x minus 3 times this other part here, 2x plus 2. And I could distribute this, right? But I don't think they'll be that complicated. We distribute this top part, we get, maybe put a fraction here, this is 4/3, whatever, it's all fine. This is fine. But even this completely laid out, all laid out like this, that's also completely acceptable. All that's fine. When you're doing these problems in the homework, if you check your answers and you see that like what you have is different than what they wrote, you can, like before, send me a message on Remind, and you can ask me if what you did was okay. See if it's the same thing. Probably will be fine. They probably simplify their answers in the book, but send me a message on Remind if you have a question over the weekend or whenever your homework is happening. All right, so that's the chain rule, the general rules. Let's look at another class of functions that use the chain rule. And this is trig chain rules, trig functions. They love using trig functions with the chain rule because it's very easy. And also other types of functions. So we know that, for example, trig function derivatives, that's called derivatives. Derivatives. Trig function derivatives. So if you look at that paper on our Schoology page, if you have that printed out or if you have it open, the trig functions in the middle there, you're going to need to know how to find all these derivatives of these trig functions, all 6. Sine, cosine, tangent, secant, cosecant, cotangent, all 6. So I'm going to give you a little bit of tricks to remember how to do them. For sine, the derivative of sine of x is just the cosine. That one you just got to memorize. The derivative of cosine of x, is negative sine. Okay, and this is going to be the start of an important rule. Cosine was negative. The sine was not. Cosine was negative. one important rule is that if it starts with a c, if it starts with a c, its derivative is negative. All of the co-functions, cosine, cotangent, cosecant, all of the c ones will have a negative derivative. That's our first sort of pattern here that we can see. So derivative of sine, derivative of cosine. All cosines will, all the code will be negative. Let's look at tangent now. The derivative of tangent of x is secant squared of x. The derivative of tangent is secant squared. So we're going to kind of learn some connections here. We know that tangent is connected to secant. Secant and tangent go together. The derivative of tangent is secant squared. So there's like connections that we're going to have with these trig functions, these trig derivatives. Tangent goes with secant. So this is all the basic ones, sine, cosine, tangent. Let's look at the other ones. Let's secant. The derivative of secant is secant x times tangent x. Secant x times tangent x. So another little rule is that for the secant and cosecant, they are doubled. Doubled. Like the derivative of, come on now, what? Can draw an E. Like the derivative of secant has two pieces for its derivative. Secant is secant tangent, right? We said secant and tangent go together. The derivative of tangent was secant squared. But the derivative of secant is secant x times tangent x. And if we look at the cosecant, derivative of cosecant, that's going to be cosecant. Like I said, the secant and cosecant are doubled. There's cosecant times the cotangent of x. And so the last little rule, I'm going to do this in, what color am I going to do this in? Yellow is a bad color. I'll just do red again, that's fine. The derivative of cosecant, the last connection we have, is cotangent and cosecant are connected together. Just like tangent and secant are together, cotangent, cosecant are together. Secant is secant tangent, cosecant is cosecant cotangent. But there's something we're missing for cosecant. What was another rule we said? What was our other rule in red? If it starts with a c, the derivative is negative. So the cosecant derivative is negative cosecant cotangent. Combination of rules. Cosecant is negative cosecant cotangent. Secant is secant tangent. And our last one, cotangent, derivative of cotangent, just like the tangent, it's cosecant squared of x. And because it's a c, it's negative cosecant squared. So these are the derivatives of the all six of the trigonometric functions that you will need to memorize. These little patterns, right? All of the c's are negative. Tangent, secant go together. Cosecant, cotangent go together. I told you we'd be running this semester. No rest for the wicked, right? And I still have 20 more minutes. Fantastic. Fantastic. All right. Derivatives of trig functions. Oh, I'm working with your it's the ADA for AP Calc. AP Calc ADA. All right. Sine, cosine, tangent, secant, cosine, cotangent. We should be able to do all the derivatives of these now. We have all these derivative rules. Tangent, secant squared. Cotangent, cosecant squared. Secant, cosecant, right? Have these patterns. Secant, tangent, secant, cotangent. Get all those together. Let's try an example. What if I want to find, if my function, f of x, let's say it is the sine of 3x squared. What if I want to find the derivative of this? The derivative of sine of 3x squared. This is going to be a chain rule. I need the chain rule. My outside of this function is the sine part. The sine here, this whole sine function, is my outside. The sine of this 3x squared. And this 3x squared part, this is going to be my inside. So I'm going to do a chain rule with my trigonometric derivative. Well, we're playing Civilization AP Calculus, so we'll increase your, what is it? Increase your I don't know what Civilization uses. Anyone play those Civ games? Get your tech tree improved, Pariso. All right, sine, the derivative of sine of 3x squared. We're going to do the derivative of the outside times the derivative of the inside. That's our chain rule. Derivative of the outside times derivative of the inside. So the derivative of the outside part, what's the derivative of sine, everybody? Look at your list, look at your rules. What's the derivative of sine? Thank you, Lizette. Cosine, yeah. So we're going to have this be cosine of, I leave the inside part alone. Leave it alone. Only do the, I should do some blue. Do the derivative of the outside part first. Derivative of the outside only. And then leave the inside part alone. I did my derivative of the outside part. Now, times, I multiply, times the derivative of the inside part. My inside is this 3x squared. So my derivative of 3x squared, I use my power rule, 3 times 2 is 6x. Thank you, Perry, so exactly. And there you are. That's your derivative. Derivative of the outside times derivative of the inside. All right? Not too crazy. Yet. Let's look at another one here. What about that's a good one. What about, ooh, I like that one. What about my function? What if my function was cosecant of, cosecant of 3 minus 5x squared. How do I do this? Well, I've got an outside part and I've got an inside part. I've got actually two outside parts. Well, here we have a triple layer chain rule. My very farthest outside part, the most outside, is this squared, right? It's like I have it in a parentheses. It's the whole thing being squared. So that squared is the most outside part that I have. That squared is the outside part. And then I've got my next inside part, which is the cosecant part. This part here is inside number 1. Inside 1. And I guess I'm going to do it in red. This part here is inside 2. It's supposed to say inside, everyone. Inside 2. So I have a triple layer part here. Inside 2. So I'm going to do my derivative of this using my chain rule. I'm just going to step through it piece by piece. Just process it in pieces. Do the derivative of the outside. My outside first is the squared part, so I'm going to do my power rule. 2 goes in front, times, I leave everything alone. Cosecant of 3 minus 5x. That's my derivative of the outside. 2 to the power, right? The power of 1. Not yet, Lisette. That's a good idea. I haven't done the derivative of cosecant. I didn't do the derivative of the cosecant part yet. I did the squared derivative. I did the derivative of the power rule first. It will be negative when I do the derivative of the cosecant part, which I'm going to do now. Right? This is my inside part number 1. I haven't actually taken the derivative of cosecant. I'm just using it because it's my inside part. We did the derivative of the outside, which is the 2, times, now I'm going to do my derivative of the inside. I'm doing the derivative of cosecant. And what was the derivative of cosecant? Look at your chart, everybody. What's the derivative of cosecant? Which ones go together? Cosecant goes with cotangent. Cosecant, cotangent, those are tied together. Exactly, negative cosecant, cotangent. So it's going to be negative cosecant of the inside part that I leave alone. I, again, leave this part alone. 3 minus 5x. Oops. Negative cosecant cotangent of 3 minus 5x. I leave it alone in both pieces. That's my derivative of the cotangent part. Of the cosecant part. Did the derivative of 2, my outside derivative, leaving the inside part alone, times derivative of cosecant is negative cosecant cotangent. I leave the inside parts alone. And now, my last part, I multiply by the inside of the last part, the derivative of the inside part. What is the derivative of my 3 minus 5x part? What is the derivative of this, 3 minus 5x? What is the derivative of 3 minus 5x? Negative 5. Very good, everyone. Negative 5. Perfect. So there's my derivative. All these pieces together. If I want, and it's very, you know how to do this, I can simplify. And it's probably important to do because checking the work. So to simplify, I look for all the numbers that are like floating around on their own. This 5, this negative 5 here. This 2 is a number that's floating out. These are going to multiply. And in fact, this negative 1 is also a number part. That negative 1 is also a number part that's going to be, that negative sign is a number, right? That negative sign represents the number negative 1. So that negative 1 this -5 and that 2 are all going to multiply together. Because all of this is just multiplying. I'm just multiplying all the pieces. -5 times -1 is 5. 5 times 2 is 10. Out there. And then I'm just going to put all the cotangents in a row. Cosecant of 3 minus 5x times another cosecant, times another cosecant of 3 minus 5x times cotangent of 3 minus 5x. And that's my derivative. It's not negative. It's not negative. Why is it not negative? Where'd the negative go? What happened? Yeah, negative times the other -5. Yeah. That. It was negative here, but because we had this -5, both negatives canceled out. Good eye. Good eye checking. These are important questions to remind yourself of. Yes, it should be negative. Why is it not negative? Am I making sure it's negative? Make sure I have the right sign. On your own. We'll come back and check these out in a couple minutes. So here's an example. Try these right here. Let's do number 1. 5 times 2 minus x cubed to the 4th power. Number 2. Let's do square root of the sine of x. Nope. Square root of tangent of x. And number 3, let me zoom out a little bit. Number 3, we'll have Jessica, you had a really good question. I'll address that in 1 second. Let me just finish this number 3 here. Number 3, how about we do, what's a good one? Like this. Let's go with four secant squared of x of 3x squared. 3x cubed. Hold on. Good. 4 secant squared of 3x cubed. Let's try this. So what Jeff was saying, the question was, for the two cosecants, since they're the same, couldn't we combine them together? Yeah. It'd be 10 cosecant squared of 3 minus 5x. And that's the same as cosecant of 3x minus 5 squared. Cotangent of 3 minus 5x. So this is also probably a more correct version. Cosecant squared. Remember, when we have like sine squared, sine squared of x, that's the same thing as the sine of x, the whole thing being squared. Just a little note here. Sine squared, when the squared is like inside, it means you're squaring the whole thing. It is not the sine of x squared. If we have sine of x squared like this, this means it's the sine of x squared. The parentheses here are extremely important with trigonometry. Typically when we have the squared just on the outside, it means that just the x is being squared, not the whole thing. That's how we differentiate between these two things. We should do it here. If I had sine of x squared, that means sine of x squared. So a little bit of information here, the two different ways we identify. Okay, give these 3 questions a try. Take out 5 minutes, and we'll check what they are in a second. If you have a question, let me know. And do we have answers for some of these? Start going over these. All right, let's go over them. I don't want to keep you too long after our class is over. So if you don't have them finished, need more time for number 3. Yeah, number 3 is a little complicated. Let me go over 1 and 2 while you're doing number 3. But again, I'll have the recording of this so you can go back and check it. I'm gonna do number 1. Let's make sure this is correct. So for number 1, anybody want to? Well, we'll try it, Lizette, and it'll be due sometime next week. Let's do number 1. Our chain rule, right? We do the derivative of the outside times derivative of the inside. So the outside part is, of course, the power of 4, right? 20. Very good, Perry. So yeah, exactly. We got 20. 5 times 4 is 20. 2 minus x cubed to the power of 3 times the derivative of the inside is negative 3x squared. Very good. Now we could simplify this a little bit more. That negative 3 and the 20 can get together. That's really negative 60. 2 minus x cubed x squared. Or sometimes the x squared in front here. That's also perfectly fine. Doing a little simplifying, right, with the number parts. Look at all the pieces together, right? All the pieces. Number 2, square root of tangent of x. So I have a derivative of the outside times derivative of the inside. My outside is my square root part. My inside is my tangent. If we remember our pattern for square roots, the derivative of a square root is 1 over 2 square root of the same thing. So I'm going to leave that as my tangent of x. 1 over 2 root tangent of x. That's my derivative of the outside times the derivative of the inside. Derivative of tangent was the secant squared of x. So when I simplify this, secant squared goes on top over 2 radical tangent x on the bottom. That would be my derivative of square root of tangent. Secant squared x over 2 radical tangent x. Okay? A little bit of simplifying, a little bit of following our chain rule. Derivative of the outside times derivative of the inside. And the derivative of tangent was secant squared. Okay? So, things that are complicated. Number 3, we have a multi-layer section here, right? We have our secant squared. To rewrite this, if you like, this is 4 secant of 3x cubed, and then the whole thing being, well, not the whole thing, I should say, just the secant part being squared. So we have here of the power of 2, the first inner layer of the secant, and the last inner layer of 3x cubed. So to do this, our power rule first, 2 times 4 is 8. Leaving the inside alone, secant of 3x cubed. Squared becomes a power of 1. So that's my first outside times derivative, my first outside. Multiply this by the derivative of the inside. Now I'm on my secant layer. The derivative of secant. That was secant tangent, right? So secant of 3x cubed times tangent of 3x cubed. That's my second layer. Secant 3x cubed times tangent 3x cubed. So the derivative of the outside times the derivative of the inside times my third layer, derivative of the very inside, 3x cubed. That's going to be a 9x squared. So my 3 layers here for this tangent, for this derivative, going layer by layer, piece by piece. If I want to simplify, I have the 9 out front here, no number here, and 8, and 9, 72 x squared secant squared, like we had before, of 3x cubed, goodness gracious, cubed, times tangent of 3x cubed. And that would be, right, our two secants multiply together, make a secant squared, tangents there, then the x squared go in front, putting all the pieces together. That would be our derivative for that one. F prime. All right, everybody. Oopsies, wrong. So a little bit of practice. Your assignment over this weekend. I'm going to change it slightly. What did I say? I want you to do, please, it's page 140, page 140. Page 140. Numbers 9 through 53, every other odd. So it's not as ridiculous. Every other odd. Try those questions. Oh, look, we're at the very end. Perfect timing. We're going to go over this. We will go over this on Tuesday, this assignment. But practice these chain rules, practice doing your drill. You will also have to use some product rules, perhaps, or some quotient rules. So don't forget any of those as well. Quotient rule, product rule, chain rule. Use all the rules to find all the derivatives, including some of the sine cosine rules. All right, folks? Good luck. Good job today. Thank you all. 140, page 140. Just 140. Page 140, numbers 9 to 53, every other odd. In your little black books. Thank you, everyone, for your time today. Hit the ground running. Get those gears turning. I will see you next time on Tuesday. Message me over the weekend. I'm happy to, I'll be on remind. Hit me up in the chat. Say goodbye. Once you say goodbye, I'll see you next time. Have a good weekend. Till next time, everyone. Thank you very much.